Okay, well, thanks very much for joining us today for the third session of NOAA's Global Monitoring Lab's virtual GMAC, or Global Monitoring Annual Conference. It's a 9-week series that we're having, trying out a virtual format as a way to share our latest science during the COVID-19 pandemic. In today's session, we'll have 7 14-minute presentations, 12 minutes for slides, 2 minutes for question and answers, with a minute to transition. Please turn off your video to save bandwidth. If you have questions for a speaker, try to add your question to the chat box and do this as the questions arise so that we can be prepared once the speaker stops speaking to be able to facilitate posing those questions to the speaker. And having said that, our first speaker is wonderful. Next, we'll move to Stein now. Stein's pursuing a PhD at Wageningen University. Let's see if I can get that right. For almost 4 years now, and he'll finish very shortly, maybe in a couple of months. And we were fortunate enough to have Stein in Boulder for a few months' time, a couple summers ago. So Stein, take it away.
Yeah, thanks, Steve. So I'll be talking today a bit about the project I've been working on now for a few years, and mainly the last results. So that the project concerns how to constrain the atmospheric oxidative capacity, mainly using metachloroform. And in our last effort, we've used a 3D model inversion for this. So to give a bit of background to that, there's a bit more delay than a few seconds, I think, but that's okay. So the problem of, so I say atmospheric oxidative capacity, but I'll mainly talk about OH, which is the main atmospheric oxidant. And it's involved in the removal of many pollutants. So a few are shown here, where you already see quite a variety because CO and NOx are kind of urban air quality pollutants, and methane is a global greenhouse gas. And the problem is that it's very important, but that OH is also, because it's so reactive, very short-lived, very variable, which makes it difficult to measure directly and almost impossible to extrapolate those direct measurements to meaningful scales. So one solution to the problem, and the one I'll discuss, is to estimate OH indirectly by studying other tracers. And the basic idea behind that is to look at the growth rate of other tracers, and then when it's that are removed by OH, and then when a tracer is growing a lot in a year, then maybe OH was low, and vice versa, which is very simplistic, but that's the basic concept. Oh shit, sorry. So as my title already introduced, there's one very good tracer for this purpose, which is metachloroform. And the reason that metachloroform is so ideal is that, well, you can see its atmospheric evolution already here, and a very notable aspect of that is that metachloroform has been declining very quickly over the past 2 decades, or maybe more. And the reason for that is that it's purely anthropogenically produced, and its production was banned in the Montreal Protocol very efficiently. Apparently there were good replacements for it, so it started to decline because the emissions stopped. And metachloroform is mainly removed by OH against a lifetime of about 5 years. And it's maybe not super clear to see from this picture, but the decline rate is about 20% per year. So indeed, this indicates that the emissions have been very low. This means that the metachloroform budget is no longer dominated by emissions, but rather it's dominated by OH, and there's a very direct link between the variations in the rate of decline of metachloroform and OH. And so that's something that we're trying to exploit in this analysis. And I'll mainly be concerned with the period after 1998, which is a period after which the decline rate has been relatively constant at about 20% per year, which makes it somewhat easier to make the link with OH. So metachloroform has been used a lot, but one thing that is new about our analysis is that firstly, that we use a 3D model inversion, but a 3D model inversion that covers these 2 decades after 1998. So before, there's been studies in simple box models, but yeah. And these are the technical details. I don't want to go into pay too much attention to it, but one important thing is that we not only adjust OH such that we fit the metachloroform observations, but we also allow for adjustments in the metachloroform emissions. Because while they are very small, we cannot really assume that they are well known or zero, because because it's very difficult to 100% certain be 100% certain that they are zero. So I wanted to talk about 2 aspects of the results, and this is the first one. So these are variations in the total oxidation of metachloroform, and for the purpose of this talk, you can treat them as variations in OH. So when you look at the y-axis, one thing is clear, and that's that the variations are not so large. So we don't need very big variations in OH to fit our metachloroform observations, only a few %, and that there seems to be no very strong trend. So the trend is very small compared to the variations. I don't want to discuss too much why there are certain peaks and certain troughs in this talk, although, yeah, there are reasons, of course, for the variations that you see here, but the important takeaway from this picture is that the variations are not so big, and that there's seems to be no clear trend in OH. So that's the first aspect. The second thing that I wanted to talk about is a bit more complicated. So what I've shown before are the global mean adjustments in OH. But what I show here is the latitudinal distribution of these anomalies in OH. And so on the y-axis, you can see the latitude, and on the x-axis, you can see the time. And then the color indicates, so red colors indicate where the model adds OH to the prior OH distribution, and the blue colors indicate where OH is removed from the prior OH distribution. And what you can clearly see from the scale of the color bar is that while the global variations are only a few %, spatial adjustments are on the order of tens of %. So they are a lot bigger than the global mean variations. And another thing to note is that the adjustments seem to be pretty systematic in that there seems to be a tendency to add OH to the tropics and to remove it from the extratropics. So, of course, because we use observations to derive these variations, the explanation for these variations is in the observations. So why is the inversion trying to add so much OH to the tropics? For that, we need to look at the metachloroform observations. And so here I show what is obviously a sketch of the latitudinal distribution of metachloroform. So the x-axis shows the latitude, and the y-axis shows the metachloroform abundance. And a very interesting aspect of the latitudinal distribution of OH is that of metachloroform is that it has a tropical minimum. And this is because OH is highest in the tropics, and the metachloroform budget is dominated by OH. And then you can also see that there's still some slight interhemispheric gradient in that metachloroform is highest in the northern hemisphere because there's some emissions going on still. But the dominant aspect is a tropical minimum, which is only a few % actually, so it's a bit zoomed in on in this picture. Now, what is going wrong in the model and why we find these big OH adjustments is that we do not quite capture this tropical minimum. So we do find a tropical minimum, but it's not quite deep enough as what we see in the observations. And so the way our inverse system is trying to fix this is by adding OH to the tropics, because then you get a deeper tropical minimum and you get closer to what is being observed. And while that is, we cannot really out of hand exclude this as an explanation. The problem with this is that I've shown before the adjustments in OH are about 30%, and they still do not quite explain this bias, this underestimate of the tropical minimum. So we need adjustments in OH of about 60 to 80%. which seems a bit large. I mean, the OH distribution is uncertain, but I'm not sure that it's that uncertain. So we started looking for alternative explanations, and there's multiple possible explanations, but I only have time to discuss one, which is which is that there might have been changes in the ocean-atmosphere exchange of metal chloroform. And what do I mean by that? Well, basically, I've only talked about the metal chloroform sink being OH, but there are other sinks, and a very small sink, but significant, is that metal chloroform can be absorbed by the ocean. And in our model, we include this as a first-order sink. So the sink is proportional to how much metal chloroform is directly above the ocean. And it varies a bit. The uptake rates vary a bit with latitude. So in the warm tropics, the uptake rates are a bit higher. But the basic idea is that the ocean is a sink to the atmosphere everywhere. And kind of the implicit assumption underlying that is that oceanic hydrolysis is fast. So what happens is that metal chloroform is absorbed, taken up by the ocean, and then inside the ocean, the metal chloroform is hydrolyzed at a certain time scale. And if you model it as a first order sink, then you assume that this hydrolysis is very fast, so that the ocean can continue to act as a sink to the atmosphere. And what is actually the case, and this has been hypothesized actually quite a while ago already in a paper by Paul Wemberg et al., is that the hydrolysis rates in the warm tropical oceans are indeed pretty quick. So the metal chloroform lifetime is about 1 year, which is quite low compared to the atmospheric lifetime of 5 years. So there, the ocean indeed continues to act as a sink no matter what happens in the atmosphere. But at the high latitudes where the oceans are cold, the hydrolysis rates are a lot lower and very uncertain, but an order of magnitude lifetime of metal chloroform will be 50 years. So obviously that's a lot longer than the atmospheric lifetime. And key to that is that the atmosphere is relatively well mixed or mixes relatively quickly compared to mixing in the ocean. So what happens is that when the emissions drop, the atmospheric metal chloroform starts to decline, as we've seen, with about 20% per year. But the oceanic metal chloroform at the high latitudes remains kind of constant on a time scale of years because the lifetime is so long. So while the tropics can continue to act as a sink to the atmosphere, there's a buildup or a relative buildup compared to the atmosphere of metal chloroform at high latitudes, which might induce a reversal of the ocean atmosphere flux. So metal chloroform is now being released from the ocean into the atmosphere. So this is basically a hypothesis from this paper by Paul Wemberg, but now we seem to find evidence for this also in the atmospheric distribution of metal chloroform. So what happens when you change from a first order ocean sink to a sink in the tropics and a source in the high latitudes is that the tropical minimum deepens because you, both in the northern and in the southern hemisphere, you start to add metal chloroform at high latitudes relative to the tropics. So the tropical minimum deepens, and this is exactly what we need to explain this bias. And actually the sensitivity of our bias to this ocean atmosphere exchange is a lot higher than sensitivity to OH adjustments. So this is why we think it might be a more likely explanation than an 80% adjustment in the spatial distribution of OH. So yeah, I was saying I wanted to make 2 points. Those are the 2 points. We have derived a 20-year time series of OH variations from metal chloroform in a 3D transport model. And we can, on a global or hemispheric scale, we can kind of fit metal chloroform observations with interannual OH variations of a few percent. But we are having some trouble with reproducing the spatial distribution of metal chloroform. So for this, we might need oceanic release of metal chloroform at high latitudes. And to link those 2 things, I would expect that the ocean atmosphere exchange of metal chloroform kind of varies on long time scales, whereas OH can vary on interannual time scales. So I still think we can leverage interannual variations in the metal chloroform rate of decline as being sources of information for OH. It becomes more problematic when we want to derive a trend in OH. So then this ocean source might become more important because we don't really know how it varies on a decadal timescale. So yeah, that's kind of the gist of it. It's very conceptual. There's the way I presented, there's still a few holes, but if you're interested, then I'm trying to submit it to ACP this week. So you can probably view it in discussion pretty soon. That's it. Thanks.
Wonderful, Stein. Thank you. I think we have a question from Lei.
Hi. Very interesting. I have a question related with the tropical minimum. It seems like the spatial adjustment largely associated with this tropical model simulation is larger than the tropical observations of methylchloroform. But I don't remember we have lots of amount of observation over that area. So how accurate you think the observation represent for that tropical region?
Yeah, so it's a good question. Typically, I think, so what we use actually, I'm not sure if I've mentioned it, but we use NOAA surface observations. And typically we assume that surface sites of NOAA are representative of a large air mass. So when I say we underestimate tropical concentrations, is that, or we overestimate tropical observations actually, is that we overestimate concentrations at Samoa and at Mauna Loa, Kumakai. So Samoa in the southern hemisphere and Mauna Loa in the northern hemisphere, which are, yeah, I mean, they are not 0 degrees latitude, but they are supposed to be representative of tropical conditions. So that's where the information is coming from.
Okay, Stein, thank you. Thanks very much for that. Next, we're going to move to Dr. Mindy Neiswanger. Mindy's an NRC postdoctoral fellow in the halocarbons and atmospheric trace species group in GML. She received her PhD working at the University of California, Irvine's Earth System Science Department in 2019. And she's interested in understanding climate-driven changes to the biogeochemical cycling of trace gases in both the modern and paleo atmospheres. Mindy, please take it away.
Awesome. Thank you, Steve. Yes, so today I'm going to talk to you all about investigating the drivers of interannual variability in methyl bromide atmospheric levels. And I just want to highlight that this is work that I'm doing with Steve at NOAA GML, as well as a lot of the modeling work I'll talk about near the end of this presentation. I'm having some assistance from Eric Saltzman, who has done a lot of methyl bromide modeling in the past. So what is our motivation for doing this work? Well, the big thing is that as we move forward into the future, the big players in terms of ozone depletion are going to decline, right? We pretty much understand that the emissions are controlled now. And as we move forward, then the naturally emitted ozone depleting substances become more important in terms of the amount of, for example, equivalent effective chlorine in our atmosphere. And so here I'm showing you a figure from the scientific assessment of ozone depletion from 2018. And you can see that the purple colors here are methyl halides, so methyl chloride and methyl bromide. And those levels are projected to stay pretty constant throughout the rest of the 21st century. But that may not actually be true. So what I want to point out here is that the climate of 2050 will not be the same as that of 1980. So when we talk about getting back to 1980 ozone levels, we're not really necessarily thinking of how climate change may impact the levels of these naturally emitted ozone depleting substances like methyl bromide. So if you're not as familiar with methyl bromide as I am, I just want to give you a little background of the budget of methyl bromide. So now methyl bromide is a mostly naturally emitted gas. So at the bottom here, I'm showing you the sources of methyl bromide. And these are the sources based on the 2009 budget analysis by Sherry Von Lewis and others. And so you see that there's sources from anthropogenics and fumigation, and these terms are controlled by the Montreal Protocol, and we expect that some of these terms have declined since this 2009 budget. There's also a significant component to the budget from biofuel and biomass burning. The oceans also act as a source, terrestrial sources as well. And then there's this missing source, which Sherry Von Lewis needed in order to balance her budget. And so when we go up to the sinks, you see that the main sink, or the main removal of methyl bromide, is from the hydroxyl radical. There's also some loss to the stratosphere, and the ocean also behaves as a sink. So when we talk about the ocean, it's important to consider the net flux between the ocean and, between the sink of the ocean and the source of the ocean. And so in this budget analysis, the ocean was behaving more as a sink. And as we move forward into the future, especially right now, we think that the ocean may actually be behaving as a source of methyl bromide to the atmosphere. And methyl bromide is also lost from soil uptake. And so as we look at this budget and we think about climate change, there's a lot of aspects of the budget that could be impacted by changes in our climate system. And so it's important for us to understand how those different systems may be interacting and impacting our methyl bromide levels. And so here I'm showing you the annual mean methyl bromide from the northern hemisphere sites in red, the southern hemispheric sites in blue, and then a global average of those sites in purple. And so our time period of coverage here ranges from 1995 to about 2019. And you can see that overall methyl bromide levels are decreasing in the atmosphere, which is what we'd expect given the Montreal Protocol and the phasing out and of the production uses. But what you'll also notice is that superimposed on the decline are some of these variations where we have increases in methyl bromide globally during certain time periods. And the two I want to emphasize are here highlighted with the shaded area. The first being 1997 to 1998, and then the second being 2015 to 2016. And we see that methyl bromide globally increased. And so what was causing this increase is something that we're going to try to explain. So my driving research questions here are, what is causing the interannual variability in the methyl bromide, as well as the methyl chloride levels? I'll talk about that in a second. And we know that it's most likely natural based on the budget. So how will that process change into the future? And so I just quickly want to mention that we are also very much interested in methyl chloride. And as you can see here on the right, methyl chloride has a lot of interannual variability. And if you were to correlate methyl bromide and methyl chloride together, they co-vary during the same time periods. And that's probably because they share similar sources. So what I wanted to do is think about what are the drivers of interannual climate variability. And many of you may have picked up on those two time periods. Those were actually big El Nino years. So we know that the El Nino Southern Oscillation, or ENSO, drives a lot of our interannual climate variability. Some of the things it drives are fires, the location, extent, and severity of fires. It changes our ocean, right? The major factor, the major thing that we look for when we're going into an ENSO year, or an El Nino year, is changes in our surface temperature in the Pacific Ocean. And it also impacts our land. So here's a diagram showing you how the wintertime pattern over North America changes during an El Nino year. So it changes the location of our pressure systems, it changes the location of our precipitation, and ultimately could impact the changes in the soil uptake term of methyl bromide. And so first what I wanted to do is say, okay, well, we know ENSO is a big deal. Do we see a correlation with our surface data? And so here I'm going to show you a two-panel plot. I want you to focus on the bottom first. So what I show you here in orange is the ENSO index. I'm using the multivariate ENSO index for this purpose. And then in blue is the methyl bromide growth rate at Mauna Loa. And so what you can see is over our 25-year time period, we can see that there does appear to be some correlation with the ENSO index and our methyl bromide surface data. Now, it does appear that there could be some lag time between our ENSO and our methyl bromide, which would make sense given that when you have an ENSO event, it takes some time for the impacts of ENSO to propagate through our climate system. And so what I did is in the top panel, I wanted to explore when I actually had the strongest correlation between ENSO and methyl bromide at a lag time. So in purple, I'm showing you the correlation coefficient, or R, for a given lag time, and that's what the horizontal axis is. So I find that the strongest correlation with ENSO and methyl bromide happens at about a month lag of 10 months with an R max of 0.73. So that says that we can explain about 53% of the variability at Mauna Loa with the ENSO index alone, which is pretty encouraging. So now we know that ENSO has some correlation with methyl bromide. Then I want to dig a little deeper and say, okay, what aspect of ENSO is causing the variability we're seeing at methyl bromide? So the first one is fire. There's some pretty good estimates of fire emissions through time. I'm showing you the Global Fire Emissions Database, or GFED. So again, on the bottom panel in orange, I'm now showing the fire emissions, and this is the growth rate of the fire emissions. And in blue, again, is the methyl bromide growth rate at Mauna Loa. So maybe not as obvious that there's a trend, or a correlation, excuse me, but if we do the same type of analysis where we allow for a month lag, we find that the strongest correlation is about 0.7 at a month lag of 8 months. So this is really encouraging. It's saying that we can actually determine that a lot of the changes in interannual growth in methyl bromide is being caused by fire, but we can only explain about 50% of the variation in methyl bromide. So what else could be causing changes in methyl bromide? And in order to do that, we now need to look into a box model type of perspective, because we know that when you change sea surface temperature, you can change a lot of the oceanside chemistry and parameters of the methyl bromide budget. So I'm not going to get into too much detail here. I'm happy to discuss with anybody who's interested offline, but basically the model is a 6-box atmospheric model at 30 degrees zonal latitude bands, and underneath the atmospheric side, we have a 2x2 gridded ocean with all of the parameterization of the methyl bromide chemistry. And so the point of using this model is so that I can look at each source or sink and hold everything else fixed to just see how much changes in each of these sources and sinks impacts the amount of atmospheric methyl bromide. And so there's 2 ways to utilize the model. Right now we have it set up to do an inversion, which solves for emissions to match the observations. And you can see on the right panel here where I have 6 different colors, each representing one of my 6 boxes in the atmosphere. And I'm comparing the modeled mixing ratio of methyl bromide to the observations we have from the HATS group. The problem with this utilization is that it's computationally expensive, right? It takes about an hour or so to run just 1 year. And if you don't have maybe all the transfer coefficients and everything tuned correctly, then you have to run it again, right? There's also the forward time-dependent model, which uses emissions to calculate mixing ratios. The problem with this type of approach is that you need to know the emissions really well as their locations in terms of geographic distribution and their seasonal cycles. So there's a lot of things that we're still trying to tune for this model, but it seems to be working pretty well. And so just before I finish up here, I just want to show you some preliminary sensitivity tests. And I really want to highlight preliminary. I haven't really dived too much into what this could mean, but what I did here is I ran the forward model for an ENSO year, so 1998, and then I ran it for a non-ENSO year, 1995. And so the main difference between these 2 simulations is the fire source, okay? So now I'm showing you just the change in the mixing ratio in terms of parts per trillion for methyl bromide over each month of the year for each of the boxes. So each of the 6 colors is a different box. And what you'll see is that the purple line, which is box 3, which is the tropical northern hemisphere, there was a lot of change in that year because of fire. And so if I take the average change over the year for box 3, my modeled output is 0.44 ppt change. And if I compare it to our surface data at Mauna Loa, I actually see a 0.43 ppt change, which suggests that maybe fire is actually really driving all of the changes that we're seeing, at least at Mauna Loa. So I just want to wrap up with some hopeful outcomes. And I'm not going to go through all of these just so there could be time for questions. But I think there's a lot of promising work that we can do with methyl bromide in terms of understanding how climate change is going to impact our budget of stratospheric ozone and all of the things that go with it. So thank you so much for listening, and I'm happy to take any questions.
Mindy, very nice. Looks like you have some promising new results there that might pan out to some increased knowledge there very soon. Brad, did you say we had a question?
We do. This question comes from Goose Velders. Mindy, the question is, you showed the correlation between methyl bromide at Mauna Loa and fire data. Did you consider fire data in the Northern Hemisphere only?
Hi, yeah, that's a great question. So in that figure, I was comparing global fire data. You can compare whichever region you'd like, but most of the fire emissions change, especially during an ENSO event, usually come from the tropics. But if you compare any of the regions, you do see a correlation. The strongest correlation happens when you compare the global.
Very good. Does Samoa, Mindy, does Samoa also show these correlations that are similar? You mentioned that the strongest correlation is with methyl bromide concentrations as you average them globally. I presume that means that Samoa also shows strong correlations.
Yeah, so on a site-by-site basis, almost every site that is in the NOAA HATS network does show some correlation with global fire. The extent, the strength of that correlation just depends on maybe like the site, right? Samoa has some other potential artifacts that maybe are masking some of the correlation there.
Any other questions, Brad?
Yeah, if we have time for another one.
Yeah.
This one is from Lei Hu, and she asks about OH. Lei, do you want to ask that question just verbally? Or?
Oh, yeah. So I think in Sherry Ivan-Lewis et al. 2009 paper, she mentioned about the internal variability is largely correlated with OH variability as well. So I think, have you considered how the OH level may influence internal variability in your analysis?
Hi, Lei. Yeah, so I haven't quite got to that extent yet, but eventually I do want to incorporate, changes in OH and all of that. Yeah, but no, that's a great point, and I definitely have it on my list of things to do.
And then Steve, we've got one more question if we have time.
Sorry, yes, go ahead.
Okay, this is from Jim Butler, and it says terrestrial sinks could be influenced by rainfall, and temperature. Do your models capture that, or could they be captured?
That's a great question. And I haven't really thought about the terrestrial sinks yet, mainly because I've been just trying to get all of the parameterizations working. So that's why I said very preliminary results, but definitely that's a good point. And I'm going to try to add all of these things into the model.
Okay, great. Well, thanks, Mindy. Looks like we're right on time. I budgeted in a 10-minute break here for before we restart and then focus on CFC 11. So we will take a 10-minute break and restart at 9:30 Boulder time sharp. So until then, thank you. Wonderful job by the first presenters. Thanks very much. Okay, so next we have Miss Corinna Adcock, who's a PhD student at the University of East Anglia in the UK, studying ozone depleting substances. Corinna is going to give us a second talk in this little CFC 11 session. Please take it away, Corinna.
Okay, thank you. So it was recently reported that global CFC 11 emissions had increased in about 2013. That study was looking at global emissions. So the next step is to try and find out where in the world these CFC11 emissions are coming from. So we investigated East Asian emissions of CFC11 using air samples that we collected in Taiwan. We collected air samples by sending stainless steel gas canisters to Taiwan, where they were filled with air and then shipped back to us. We then measured them using an auto-spec GCMS for about 50 trace gases, including CFC11. Air samples were collected every year between 2014 and 2018 in the spring of each year. And usually either 1 or 2 samples were collected each day. And in total, 135 samples were collected across the whole of the 5 years. There were 2 sampling sites in Taiwan. In 2015, samples were collected at a site on the southern coast of Taiwan. And then in all of the other years, samples were collected at a site on the northern coast of Taiwan. Both sites should be influenced by relatively similar outflow from the East Asian mainland. These are our CFC11 measurements from Taiwan. I have also included CFC11 mixing ratios from Mauna Loa in Hawaii for comparison. They are the coloured squiggly lines going along the bottom. You can see that sometimes the CFC11 mixing ratios in Taiwan are similar to what they are in Hawaii, but sometimes they are higher. And higher CFC11 mixing ratios are an indication of CFC11 emissions from relatively nearby sources. So what we want to do is investigate where this CFC11 is coming from. We investigated the history of air arriving at the sampling sites using the UK Met Office's NAME, or Numerical Atmospheric Modelling Environment Particle Dispersion Model. The model was run using 12-day backward trajectories for when each sample was collected. Then, in order to quantify the contribution from various regions, the model domain was divided into 15 regions using shapefiles produced by ArcGIS, a geographic information system. The output is a mass density residence time, which is the sum of the particle concentration in each grid cell for each second. This was then used to investigate the influence of air from different regions. We then looked at the correlations between the influence of different regions and the CFC11 mixing ratios measured in Taiwan. For all years combined, the strongest positive correlation was between CFC11 and NAME particle counts from East China, with an R value of 0.495. All of the other regions had weaker correlations with R values of less than 0.3. This suggests that East China is the likely source region of the CFC11 emissions. East China is a major industrial area, and it has been previously identified as a source region of other chloromethanes, such as methyl chloride and carbon tetrachloride. East China was also identified by another study by Matt Rigby and co-authors as a likely source region of CFC11. After looking at the source regions, we then looked at the correlations of CFC11 with other trace gases that were measured in the Taiwan air samples. The compounds that had the strongest positive correlation with CFC11 for all years combined were chloroform, carbon tetrachloride, HCFC 141b, HCFC 142b, dichloromethane, and HCFC 22. The correlations between CFC11 and these compounds are likely due to the co-location of their emissions in eastern China. We then estimated the size of the CFC11 emissions using this equation. So we took the slope of the trend line of CFC11 mixing ratios plotted against the mixing ratios of halocarbon X. Halocarbon X being a compound that had a good correlation with CFC11 in the Taiwan samples. We then multiplied this by the emissions of halocarbon X, which we got from the literature, and then times this by the molecular weight of CFC11 divided by the molecular weight of halocarbon X. We ended up with 7 different emission estimates, 2 for dichloromethane from 2 different studies, 2 for chloroform, both from the same study, 2 of carbon tetrachloride, also both from the same study, and then 1 for HCFC22. Now, all of these studies used various different methods to calculate their emissions, and some of these studies calculated emissions for the whole of China and some for just the eastern part of China. We decided to use multiple different emission estimates in order to increase the confidence in our overall estimate and to also show the possible range. So these are our CFC11 emission estimates. You can see that there is quite a broad range in the emission estimates. The lowest one is 12 gigograms per year, and that's based on the dichloromethane estimate. And then the highest one is 27 gigograms per year, and that's based on the HCFC22 estimate. It's interesting to note that both the dichloromethane estimate and the HCFC22 estimate are for the whole of China, whereas the chloroform and carbon tetrachloride estimates are for the eastern part of China. So there is no clear pattern of higher emissions for the whole of China and lower emissions for eastern China. We then combined all 7 of the emission estimates together to get an overall estimate for CFC11 emissions of 19 gigograms per year, or between 14 and 23 gigograms per year. We then wanted to investigate whether the increase in global CFC11 emissions in 2013 was related to an increase in CFC11 emissions from China. As our measurements only went back to 2014, we used previously published CFC11 emission estimates in order to investigate this. So each marker on this graph is a different emission estimate, and the markers in green are emission estimates for the period between 2008 and 2011. And when we combined these together, we got an estimate of about 12 gigograms per year. Then all of the yellow values are the CFC11 emissions that we estimated in this study for the period between 2014 and 2018. And when you combine these together, as I said in the previous slide, you get about 19 gigograms per year. And if you compare these two values, you get an increase of 7 gigograms per year, or between 2 and 12 gigograms per year. The study that I mentioned previously by Rigby et al. Also estimated CFC11 emissions from eastern China, and they are shown by the red line in this graph. And they estimated an increase in CFC11 emissions from eastern China of about 7 gigograms per year, or between 4 and 10 gigograms per year, which is similar to the estimate that we calculated in this study and increases the confidence in the overall estimate. We then looked at the size of the emissions from eastern China in comparison to the global CFC11 emissions. So in this graph here, the 3 green bars are estimates for the global CFC11 emissions in recent years. And we compared this to the emissions from Eastern China that we calculated in this study, and they are about. We then also wanted to investigate how much of the recent increase in global CFC-11 emissions could be explained by an increase in emissions from Eastern China. So in this graph here, the 3 green bars are the estimated size of the global CFC-11 emissions, the estimated size of the increase in global CFC-11 emissions, and we're comparing this to the size of the increase in emissions from Eastern China that we calculated in this study. You can see the uncertainty around these numbers are larger. The increase in emissions from Eastern China can explain anywhere between 10% and 90% of the increase in global emissions. So it's likely that emissions from Eastern China did have a contribution, but we're not sure how big that contribution was. So to summarize, we investigated East Asian emissions of CFC-11 using measurements that we made of air samples collected in Taiwan. We found that CFC-11 emissions are likely coming from Eastern China at levels of about 19 gigograms per year. We also found additional evidence for an increase in CFC-11 emissions from Eastern China of about 7 gigograms per year, which likely contributed to the global increase in CFC-11 emissions. We're still not really sure what caused this increase in CFC-11 emissions, but it has been suggested that they may be due to illegal production of CFC-11 for its use as a foam blowing agent in building insulation. But further investigation is needed into the recent changes in CFC-11, as concentrations of CFC-11 need to continue decreasing in the atmosphere in order to achieve the aims of the Montreal Protocol and to enable the ozone layer to recover. Okay, and that is everything.
Thanks very much for that, Karina. Nice presentation. I have a quick question. I think we have some others too. One would be that, did you look at whether or not the different regions within your map, whether or not they were similarly sampled by the particles in the trajectory analysis? In other words, were you similarly sensitive to emissions from any of those regions so that Eastern China would show up as being different, or were the measurements from Taiwan mostly sensitive to Eastern China?
The measurements from Taiwan were mostly sensitive to Eastern China. So the measurements weren't evenly sensitive to other areas. Some areas had very little influence on Taiwan. So it's possible that you could have CFC-11 emissions in some of those areas as well, and you wouldn't be able to pick it up in the measurements in Taiwan, because they wouldn't have enough of an effect on the mixing ratios that we were measuring.
Okay. Any others, Brad?
No, I don't see any others here, and I had a similar question, so thank you for answering that anyway.
Yeah, I had one other quick one, and that was, it wasn't clear to me how you scaled the emissions estimates when your denominator was an emission estimate related to all of China versus just East China.
Yeah, so we decided to include estimates for both Eastern China and for the whole of China. And so we had our 7 emission estimates, and then we just averaged them all together. So our overall estimate is a sort of weird mixture of both the whole of China and Eastern China. In our article, we called it Eastern China, but we put the Eastern in brackets and then just used that term throughout.
Yeah.
So the estimate, yeah, like I did here, like Eastern China, but with the Eastern in brackets. So, and we did this because there wasn't a clear difference between having higher emissions for the whole of China and lower emissions for just the eastern part of China. All of the estimates overlapped, so we decided to combine them together.
Yeah. Okay, great. Brad, do you want to ask a quick one? We're running a little short on time, but.
No, I think that's fine. I think we should move on.
Okay.
But thank you. Nice talk, Karina.
Thank you.
So I'll go ahead and introduce our next speaker so he doesn't have to introduce himself. Our next speaker is our organizer, Steve Monska. He comes from the NOAA Halocarbons and Atmospheric Trace Species Division in Global Monitoring Lab, and has been, he tells me, almost 30 years at NOAA. So congratulations on that, Steve, and take it away.
Thanks very much, Brad. Excuse me. So the task for today, what I hope to discuss today, is interannual changes in global emissions of long-lived trace gases derived from atmospheric measurements, to look at those changes to understand whether or not they're reliable, whether or not we can reliably estimate those changes. There's a number of other folks who are involved in this work listed as co-authors, and certainly it's the result of a broader group of folks, including those making the measurements within NOAA and Ceres, the station personnel at remote sites around the world, other 3D modelers who've contributed, and the A-Gauge community of scientists. So here's a picture of CFC11 emissions. Each point represents an annual estimate of emission over time. And this record is derived from measurements of a dozen different remote sites around the world, and where we get weekly flash measurements. And at a subset of those sites, about 5 of them, we have in situ instrumentation. We combine those results to derive this emission history. And we do it, global emissions are derived with a simple mass balance consideration, where we have a 3-box model. If you consider the atmosphere, the rate of change in the global burden is a balance of emissions minus loss. And we measure concentrations or mole fractions at Earth's surface and how they change over time. So we estimate this term, we estimate the global burden based on the surface measurements. We think we know the lifetime or the rate constant for loss so that we can derive emissions. And this is what we get. So the question is, are these interannual changes real? And for example, typically we might have in the past suggested that if we're looking at changes and we want to know whether or not they're robustly determined, we usually average over multiple years. But we're really interested in providing more rapid feedback to understand how emissions are changing from year to year, especially for policymakers. And so when we get increases, for example, from 2013 to 14, or decreases from 2017 to 18, we really want to know whether or not these changes that we're deriving are robust. Certainly answering this question relates a lot to what we think the uncertainties are in each of those annual estimates. We estimate those uncertainties to be between 2 to 4 gigagrams per year based on a few specific things: measurement precision and consistency, the atmospheric variability measured at different sites, and an estimate of the network's ability to represent the true global surface mean. We do that with bootstrap techniques like used by Ed Duklikinski for methane. So the uncertainties of 2 to 4 gigagrams a year don't explicitly include calibration consistency from year to year. And this is significant, or potentially significant. A 0.1% error in our ability to maintain a consistent calibration from year to year would lead to a 5 gigagram per year emission error. That's substantial. But in fact, we think our ability to maintain calibration consistency is better than that, about 3 times better than that. And when we look at the annual global mean changes from year to year, the interannual change in global mean surface mole fractions between NOAA and A-Gauge, we get a similar estimate for our ability to maintain calibration consistency. The other factor playing into this is, however, variability in atmospheric transport and dynamics. particularly given that we make measurements at Earth's surface, which characterizes, presuming good, well-mixed atmosphere, up to maybe about 80% of the atmosphere, and yet the loss region is in the stratosphere. And there's variability in how air from that loss region and this emissive and that loss signal reaches the surface where we make measurements. And so it's that variability that we're trying to understand here today and quantify. And this follows on a study by Eric Ray from earlier in 2020, and it uses a similar approach where we consider the emission history that I just showed you in black, and we derive a smooth version of that emission history. And then we use that smooth emission history as input to a simple 3-box model to derive then simulated mole fractions, and we do it by hemispheric means, but also as input to 2 3D global models using different meteorology. Smooth emission history, we will see what we get back out in terms of concentration variations, and we'll assess that in terms of measured versus simulated rates of change for mole fraction. So here we have the rate of change now plotted for different years from that smooth emission history put into as input to a 3-box model with constant dynamics, constant mixing terms between the boxes. No surprise, we get smoothed rates of change derived for the northern hemispheric mean mole fraction on the left here and the southern hemispheric mean mole fraction on the right. But what happens when we do that? We use that smooth emission history into a 3D model with specified dynamics that are trying to represent real changes in atmospheric transport and dynamics from year to year. We can see that the mole fraction trends, the changes in rates for hemispheric mole fractions have an added variability. And this is the mapping of dynamical changes into CFC11 mole fractions. The next question is whether or not these variations, which are on the order of plus or minus 0.1% per year on the rate of change in the model, whether or not they represent reality at all. And I will also pose a similar question when I say we'll compare these to measurements, but an equally important question is whether or not the measurements represent reality, given our uncertainties in maintaining consistency and our ability to characterize hemispheric changes in mole fractions. So the blue line here then is what we actually derive from the surface measurements in the 2 hemispheres. And for me, I found some of the covariations, in particular here in the northern hemisphere, to be very well mapped in the simulation compared to what we've observed, where we see peaks that are derived now, presumably, or this implies that those enhancements, a slowing down of the decline of F11 during this period of time and this period of time, and over here in the southern hemisphere during this period of time, are due to variations in transport. Now, the fairly good consistency observed here since 2014 or so isn't observed for all years. For example, we have some hints of similar phasings here in the model and the measurements, but of different size, and maybe even anti-correlations here. So although the interannual variability in the model is similar magnitude, the phasing sometimes is capturing what is measured and sometimes isn't. And I would also point out the fact that some of these differences could be due to the fact that there were short-term changes in emissions, although for F11, we'd expect that those short-term changes in emissions to be rather small compared to the a slow-moving change in emissions over time. We also considered another model. The first one was a Wacom, and this one was Tomcat, using a different representation of meteorology. And you could see similar patterns arise, where both models capture this slowdown in the decline of CFC11 during this period of time in the northern hemisphere due to what looks to be dynamics, and a particularly slowing during 2015 and later on in this latter period in the southern hemisphere. There's a little better correspondence in the Southern Hemisphere in the mid-2000s, although the phasing or the magnitude is slightly different. So we have these two different models that we think are representing some aspects of dynamics that are captured by the observations and that add to variability in the rates of change that we're measuring for CFC11 and ultimately the emissions that we're deriving. So we're going to use these mole fraction simulations, the simulated mole fractions from the models, to derive then emissions and use those emissions as corrections on what we've derived from a simple box model analysis of the NOAA measurements. This is in the absence of, for example, a full-on global inversion. This is a picture of those biases that are created in emissions or that are calculated in emissions based on the 3D model results. The two colors represent the biases in emissions derived from either the Wacom model in red or Tomcat. And again, this is the difference between the emissions derived from the simulated 3D simulated mole fractions minus the smooth emission history that went into the model that was used as input. And we can see that these interannual changes in these biases typically have the same sign with these two model analyses. In other words, we're getting estimates of positive biases and lesser biases that are changing interannually. They're similarly captured in both models. The mean interannual bias is about 5 gigagrams a year, but it's as high as, for example, in 2000 here, 15 gigagrams a year. And compare this with our 2 to 4 gigagram per year uncertainty in the emissions estimate, and you realize these influences are substantial. Also note that in Wacom, this suggests a significant shift in those biases before 2000 and after, and this may reflect a known perturbation in stratospheric circulation that's been studied in a number of different papers in the past. So we then apply those biases to the uncorrected version history of emissions over time. That uncorrected emission history is indicated in black, and the corrected emissions due to those dynamical variations is indicated in red. And you can see that after 2010 or so, the emission changes derived with these dynamical corrections included are smoother. This peak in 2014 goes away, presumably because of dynamics, and the peak in 2017 is reduced somewhat. And this is in the Wacom model. Similar corrections are applied by the Tomcat model using it. Going back in time, though, further into the 2000s, it looks like sometimes variability in what is implied for emissions is enhanced during this year. And the question is this real, or is it due to enhanced errors in observations or models? That's something that we don't have an answer to currently, but hope to in the future. And so in summary, over time we've made improvements in measurement capabilities so that we think we can derive annual emission estimates with uncertainties on the order of 2 to 4 gigagrams just from the things that we have control over. But 3D models with reanalysis meteorology suggest that larger biases in year-to-year emission changes can stem from variability in dynamics, and that these biases can persist for multiple years if we look, for example, at the post-2000, 2000-2005 period. Models appear to do a fairly good job of simulating measuring interannual variability in mole fraction trends in some years, but not all. And assessing emission changes on a year-to-year basis requires an accurate estimate of these non-emissive influences on derived global emissions if we really hope to supply rapid and timely feedback to others who are interested in knowing whether or not, for example, policy decisions and actions taken have had any kind of impact on global emissions. And this is one estimate of how we go about doing this. The next talk will include an observational-based estimate of estimating these biases. That's it. Thanks.
All right, thank you, Steve. If there's any questions and you want to raise your hand, we can call on you through audio. I'll ask a question if we have a little bit of time, Steve. So I guess the question would be the interannual variability of emissions that's implied even with the dynamic corrections. Do we know enough about the emissions from foams or banks to suggest that maybe there could be interannual variability in that release through ramped up destruction of buildings and construction in places where that bank might be significant?
Yeah, Brad, that's a good question. It's really hard to know, but it's also hard to imagine that that's going to add a lot of interannual variability to the emissions. If anything, I would have expected more interannual variability after 2012, given the possibility, in fact, that new production was resumed. Yeah, I guess I'll leave it at that. We don't know a lot about how that might vary. It's a big reservoir, though, and we'd imagine that it would just slowly release these things with not much variability over time.
Okay, thank you. We're running a little bit late, so if there aren't any other questions, we should move on to our last talk.
Very good. Okay, next we have Dr. Eric Ray. Dr. Ray, Eric is a senior research scientist with Ceres in the Chemistry and Climate Processes Group of NOAA's Chemical Science Laboratory down the hall from us there in Boulder. Typically down the hall when we're in the building, which we haven't been for some time, no doubt, where he studies atmospheric dynamics and transport processes for affecting trace gases. He did his graduate work at the University of Washington, Seattle, receiving his degree in 1997, and he's going to finish up the session on CFC11 for us, using some observational studies. Thanks very much, Eric. Go ahead.
All right. Thanks, Steve. So yeah, this is a follow-on to Steve's work, and the focus here will be more on the source of the anomalies and their transport through the atmosphere, and the focus also will be on satellite measurements instead of the models. So you can see the list of co-authors here. These are the collaborators I've worked on this with in NOAA, CSL, and GML. All right, so I'm going to jump into it. Steve has given the motivation here. I'll start though with some model output, because this sort of summarizes the transport features we're looking at pretty well. So I focus on this 1 to 5 year time frame for the anomalies. The reason is that this encompasses the QBO. We know that the QBO is a dominant mode of interannual variability in the stratospheric transport. So what we have on this plot is model output of CFC11 partial pressure anomalies. So they're global averages at each level here, and then at each month. So this is height versus time. And you can see the different colors are the anomalies propagating from the middle stratosphere down to all the way to the surface. And they correspond with every QBO cycle. These are the QBO winds here in these colors. So every one in the model propagates clearly all the way down to the surface. Okay, coherent descent. So this is sort of work we've looked at, been published previously. One more plot from the model output just shows the pattern of these anomalies and how they're transported down through the atmosphere. So for CFC11, this is a composite then at the times when the anomalies are maximum at 20 millibars. So you can see a big red orangish circle here. So that's the global average is positive here. And the snapshot shows that at any one time in the atmosphere, you have a series of these anomalies propagating down from the tropics out to the high latitudes in each hemisphere and down across the tropopause and into the troposphere. Okay, so this pattern is specific to CFC11 because of where it is destroyed. So this dashed line shows the local lifetime of 90 days. Above that, it's destroyed more rapidly, so the anomalies do not propagate down from those higher levels. They only propagate from these levels. And the QBO winds shown here in the green and the pink lines are sort of equatorially symmetric, and they propagate down, and these anomalies respond. And below this line, they move down and into the troposphere. So each trace gas will have a different pattern. All right, so this is from models. What about measurements? We like models, but we also like measurements and see what they can tell us what's going on in the real world. Okay, so I'm going to use satellite measurements from ACE. So what's shown here then is the sort of sampling locations that I'm using from ACE in the stratosphere. It's all the blue squares, and the sampling of ACE is skewed towards the extratropics. So I've gridded ACE ups to account for that. That's fine actually for this study, because as we've seen, the anomalies propagate down primarily in the extratropics. And then for the surface measurements, I'm using the NOAA network to represent what's happening in the lower troposphere. All right, so I'm just going to be looking at hemispheric averages at the surface. So that's shown here. We assume that the NOAA sites represent, a lower tropospheric hemispheric average essentially. And so we're sort of connecting what's going on in the stratosphere by the ACE measurements to what we see at the surface. And there's a bit of a gap in altitude, but the ACE measurements extend down roughly to the tropopause. So they get through most of the time of transport. All right, so we're going to do correlations here. And so I'm showing time series just as an example from an ACE location here in the lowermost stratosphere in blue, and then the NOAA Northern Hemisphere average anomalies. Again, these are 1 to 5 year bandpass anomalies. So you can see from this that the ACE anomalies have somewhat similar features, and they lead the surface by some amount, and it actually is a variable amount. And that's to be expected, actually. If we go back to some model results real quickly, this is the model descent of each individual CFC11 anomaly from the QBO cycles in the southern and northern hemispheres in the different colors from 30 hectopascal. This is just going down to 500. The point of this is that it's highly variable in the descent rate. So if you look at each of these individual ones, there's a big spread in time. So QBO cycles are like snowflakes. No two of them are alike. This is not conducive to correlations with a single lag time. So we're going to do something different than just correlate over the whole period with one lag. We're going to do running correlations. So essentially for each month of the time series, we're going to do a 4-year correlation, so centered around that month, plus or minus 2 years. So I'm just showing here that the correlation from every ACE location in the stratosphere with a certain lag with the NOAA hemispheric average time series. Okay, so this just sort of trying to schematically show how we're taking ACE measurements from earlier and earlier. We go back up to 48 months previous to what's seen at the surface, but it's constrained somewhat by a location in the stratosphere, how far we go back for each place. So we'll come up with a monthly resolution correlation and lag over this whole ACE time period. And what I'm going to show next is just the average of those correlations and lags over this time period. Okay. So this is then the map essentially of those correlations with the ACE measurements throughout the stratosphere with the surface northern hemisphere average measurements. All right. So what you can see here is that the maximum correlations for this case are found in the northern hemisphere lowermost stratosphere, just above the tropopause. That's right where we would expect them, because this is where we know the air is dumped out of the stratosphere and affects the troposphere in this region most directly. We can also see, though, that there are correlations with the opposite hemisphere, the southern hemisphere in this case. They're much lower than in the north, but still significant. So there is a contribution of these anomalies from the opposite hemisphere. All right, so now we can also look at the average lag times associated with those correlations we just calculated. So the lag times approximate the transport time from each location in the stratosphere to the surface. These range from 2 to 30 months in this scale, okay? So depending on where you are in the stratosphere, it takes a lot longer. The stratospheric circulation is quite slow. So you can see in the north, the transport times to the surface are quite relatively short, 4 to 10 months from this lowermost stratosphere region to the northern surface. And from the opposite hemisphere, it's roughly 8 to 10 months longer. That's consistent with what we'd expect of the sort of interhemispheric transport time within the troposphere itself. Okay, so this is really a unique information, actually. I'm going to show now the correlations then with the southern hemisphere surface. There are very few trace gases that can give us this type of coherent anomaly picture all the way through the stratosphere and maintain that at the surface. So So these time scales and locations of this correlation are quite interesting and unique, I think, to CFC11. Okay, so comparing now the southern hemisphere correlations, we can see that the highest correlations we find in this analysis are actually right at the southern hemisphere tropopause region around 60 south, and that the tropopause is shown here in the orange. It's a little difficult to define in this region, so I think where this green dot is, that's locating the max region, is actually right around the tropopause. Okay. So you can also see from this that in the southern hemisphere, there's a clear propagation pathway down from the tropics and all the way to the tropopause. And this is similar to the model, as I showed earlier, that it seemed like a clear pathway in each hemisphere in the model, right from the tropics on down. Another thing to note is that there are relatively high correlations in the opposite hemisphere here in the north to the south, right? This is consistent with what we know about the stratospheric circulation, that it's stronger in the northern hemisphere. And you can see that this location of high correlations is consistent with sort of the transport out around the subtropical jet, and then it gets caught in the Hadley cell and brought down into the opposite hemisphere. You don't see that as strongly in the south. Okay, another thing is that the northern hemisphere the correlations originate in the highest latitudes. There doesn't seem to be as clear propagation from the tropics. This could be partly to do with the resolution of ACE. And then also we see that there are different pathways in the northern hemisphere on the effect from in that hemisphere in the troposphere versus to the southern hemisphere, right? So it's a high latitude pathway down to affect the northern hemisphere, a lower latitude pathway down to affect the southern hemisphere. So these are all really interesting transport features that are revealed here. I'll go to the lags. So again, the southern hemisphere on the left, northern hemisphere on the right. Just note that, of course, it's a very fast transport time from this tropopause region, 2 to 4 months down to affect the southern hemisphere troposphere. The transport time from the tropics to the southern hemisphere surface is about 2 years. On average, this is very similar to the model, actually. So nice justification of the model results. We have relatively short transport times from the north to the south. So you can see it's getting out here relatively quickly compared to what you see from the south to the north. So again, faster transport out of the northern hemisphere, moving across the troposphere into the southern hemisphere. And also you can note that the faster transport is seen here just in how blue these times are in the north. So 6 to 9 months to just flush out the lowermost stratosphere of the north, quicker than happens in the south. Okay, so these green dots you might have noticed are the maximum in the correlations in each hemisphere. So I'm going to use these. So the patterns I'm showing you essentially are interesting. They derive, a lot of unique aspects of the transport. But when we're looking for how we can determine the sort of effect on the surface, we really want to just locate the maximum features right down near the tropopause, where we know that the influence is most similar to that at the surface. So I've identified these regions. I'm going to do linear regression for each hemisphere and see if we can predict the surface anomalies from those. All right, so this is just showing then what we're doing. We're doing a similar type of calculation as a correlation. It's a running regression and prediction. So all this is just a linear equation which shows the prediction at the surface over some 4-year time period, right, centered around each month it moves. It's a running prediction. We've done regressions based on the correlation locations for each of these 4-year periods. So those are all time dependent. We've kept constant those green dot locations essentially. So these are the time series for each of the ACE locations up in the stratosphere. And then we've lagged, very variably lagged those stratospheric locations based on the southern and northern hemisphere individually. All right, so what we end up with is each month, because we have this overlapping running correlation and regression, we have 48 anomaly predictions that can be averaged for each month of the time series. And so that's what I'm going to show here is the prediction. So the southern hemisphere surface on the left, northern hemisphere on the right. Okay, so the surface measured anomaly is in red, and the prediction from ACE is in blue. So the locations, the regressors, locations and lags are shown here down in this light blue color. So, you know, where they are located in latent pressure, and then the lag, the average lag, 4 months plus or minus 2. So that's standard deviation. We use, you know, the full range of lags that we derive from the correlations. Okay, so you'll notice there are light blue lines on here. These are each of the individual 4-year running predictions. And so the spread of those is some indication of the uncertainty of this estimate, and also the time of lag change. So you can see that the lag that got the best correlation for a previous QBO cycle didn't work as well for the next QBO cycle, perhaps. So the lag had to change enough to incorporate that change in the transport, essentially. And so the solid blue is an average then of all those. All right, so you can see very good agreement actually through almost all of these anomalies at the surface. Greater than 90% of the variance can be explained by these average predictions, so by stratospheric transport, essentially. Last thing is just if I do something like Steve showed, where I sort of bias correct the global average growth rate using these predictions, I can show you what the result is of that here in the light green. So essentially, the purple is the global average growth rate anomalies, and the green is when I've removed those predictions, okay, over this time period. So on the left axis is the growth rate scale, and on the right axis is sort of an approximate emission scale. It's not exact, but it shows you roughly the range that Steve was showing earlier. So similar to Steve's message, you know, not accounting for this type of stratospheric transport variability can bias your emission estimates by a fair amount, at least 5 gigograms in some cases. And as he mentioned, this is especially important in early detection of emission changes. All right, so I'll just finish there and say that it seems like most of the interannual variability in the lower tropospheric F11 can be explained by transport from the stratosphere, so based on these measurement data sets. This complements the model results, although it seems like we can get more consistent explanation of the variability by transport than the model, but that's not terribly surprising. This is complicated to get right. It's two plus years of transport over the whole range from the lower stratosphere through the troposphere. So it's difficult to get right. I'd say that CFC 11 is uniquely suited to reveal QBO trace gas features through this region due to a combination of the location of its loss region, lifetime, quality, and quantity of measurements. So it's really the best that I've found to do this type of work. All right, I'll just stop there. Thanks.
Thanks so much, Eric. That was great. You're right at 15 minutes. You used up all your time. But I would, and I don't, do we have any other questions that have shown up, Brad?
No. Oh, wait,
No.
there is something in here. Yes, there is. It's from Fred Moore. I'll go ahead and read it if we got time.
Sure, yeah.
From Fred, is there a way to relax the 4-year running average at the endpoints to improve the short-term predictability?
Well, yeah, I do that. I didn't say that, but I do allow down to 2-year correlations at the endpoints. So 2 years is about as short as it gets as far as this analysis. So it is somewhat relaxed, the 4-year time frame at the endpoints. That's already in here. It's hard to go any shorter than that, or you don't get a full QBO cycle, really.
All right, thanks, Eric.
Yeah.
I have a question, but I'll ask it to you at another time.
Great.
Well, thanks so much for that. And thanks to all the presenters contributing to the success of this session. I think there's a number of nice presentations, and appreciate the presenters' time for preparing the talks here and being willing to give them during this unusual time. Recording of those presentations where the presenter agreed will be made available for future viewing, and Just a reminder that the next EGMAC session will be hosted by Dr. Arlen Andrews next Monday, June 29th. And the session theme will be understanding the planetary boundary layer. And we look forward to presentations, the discussions that follow in that session. So thanks again for attending and have a great week. So long.
Thanks, Steve.
Yeah, James, thank you.
Yep, thanks, Steve. Thanks, James. That went well.
Thanks, Brad.
Yep, see you next time.
Okay.
I'll get you a copy of the questions and chat once it's available to me after the meeting.
So does Steve have to archive the chat, or will you do it?
It's been up to the chair if they want to send questions to, to get answered, or so it's
yeah.
There's no set policy for it yet.
If you could copy those and save them, James, that would be great. I forwarded one of the questions to I forget who it was already, but yeah, I'll forward on those questions to the speakers.
Okay. Yeah, as soon as I get them, I'll send them to them.
And then James, just to revise or to review, 2 of the speakers asked that their talks not be recorded, and I had that down as Lei and Xiang Li.
Yeah.
Yeah, that's what I have too.
Okay, good.
Yeah, and I'm wondering about the same. Maybe I got a 2018 value. That's all I'm worried about. Yeah, for now, maybe don't post mine as well. Would that work, James?
Okay. If you want to give me an updated slide.
An updated slide without the 2018 value?
Yeah.
All right, I'll think about that. Good.
Thanks
a lot. Yep.
Okay.
All right. So long.
Bye.
Eric, you still there? He has left the building. Okay. Bye-bye.